So in a simple way, I will write here and say total momentum must be conserved in an isolated. That's it. Total momentum must be conserved in an isolated system. So this would mean here, if for an example, during a collision, and this collision, let's say we have two masses, and for this particular example, would want to work out an example where masses do not join. So if I have this mass, call it mass 1, and it is moving with initial velocity v1 in this direction, and I have mass 2 moving in the opposite direction, that is mass 2 with the initial, so moving with initial velocity u2. One thing to do is that since the two of them are moving in the opposite direction, if we pick this to be the positive direction, automatically remember this one to make it negative because they're moving in the opposite direction. So then, before collision, total momentum here will be the momentum of the first mass and the momentum of the second mass. So here we're going to have m1 u1 added to m2 times negative u2. All right, this is negative. So once we combine that, it will be m1 u1 minus m2 u2. Our total momentum before collision. After collision, since we said do not coalesce, meaning do not join together, so let's suppose, because there are few possibilities after collision. After collision, masses may choose to do one of the following. Okay, first, if they do not coalesce, they may move in the same direction. Move in the same direction at different speeds. Okay, so another possibility, they move, this was same direction, so they may also move in different direction at different speeds. Number 3, one may be stationary, and the other moves on. All right, so moves on. And then any other possibility we may have a collision, and then let's suppose they move in the same direction like that. So we still have our m1 and this is our m2. Now after they collide, check, our positive was in this direction, so then this will be still positive v1 because it still moves in the same direction. So now it moves in that direction, so this will be what? Positive now. So finally we have, after collision, total momentum will be m1 v1 plus m2 v2. So that becomes our momentum after collision. Is that clear? So that's it. In case these are the first object, if they move in different directions, you only need to pay attention to this side of the velocity because it's a vector quantity. So you just reference to your initial positive direction, and then you can define whether the final velocity is positive or negative. Is that clear? All right. So what if they join together? When masses join together. All right. So let's suppose we have momentum on this side before, and then we're gonna have momentum after on the other side. So now, if these are still our masses, m1 and then m2, all right? Let's suppose they're still moving in the same opposite directions. So this will be our u1. Automatically, this becomes now negative u2 because it is in the opposite direction. So if they coalesce together, so we expect that this will be m1 plus m2 after they join together, and then times their common velocity. So in a simple way now, this on this side we're gonna have m1 u1. So this will be m1 u1 minus m2 u2, because of this product of negative is equals to, on the other side we're going to have m1 plus m2 times v, and the v is our common velocity.